Yes, thank you, Anil, and hello, everyone. Good afternoon. Um, Today I'm going to talk about a work that we just put in archive with Marika. I mean, leading the whole thing, and Laura and Christiana also contributing a lot. But I'm going to be talking actually about, let me call, a side product of that work. It's not really the main focuses of the paper, but so much that part of what I'm going to present is the appendix of the paper in some sense. But I thought that this setup here, this opportunity for the Hyperboloidal webinar, it's a good place to really focus on this specific part of the argument and the whole thing. So yeah, let me just give you an outline. The main topic of the paper is to discuss and understand and develop what we call quasi-normal products for the Hyperboloidal framework and everything. And so I'm going to use this as a motivation for the main topic of this talk. This is where I encountered these T5 symmetries, but they appear in many other places. So yeah, the actual result of the paper is just coming here as a motivation for the whole thing, before entering in the symmetry and how to see them in the hyperboloidal. So yeah, let's start just with, as I said, this motivation. And the context here is, well, black hole perturbation theory, especially because when we are perturbing a full solution to the Einstein's equation around some given background, let's say Kerr, and well, some notion of small parameter, we can describe some parts of the wave signal, right? And in particular here, the one that we are talking about is the ringing down, the very last one. I think everybody here has came across here. They know I don't have to introduce much, but essentially, well, you know that after the black hole merges, there is a kind of a distorted remnant, and the space-time is still radiating, is still leaking energy away until we reach stationarity. And the waves kind of decay exponentially with very particular time scales and oscillates also with very particular and specific time scales. So, and this is one of the main things that we bring hyperboloidal into the game, especially because this modeling is usually done in this, well, traditional, let's say, usually daily notion of time. But we know that geometrically, this time has a very specific feature that they accumulate at these 2 points, and this leads to consequences that, when we put in our physics, that boundary conditions carry energy away. Understanding in this way, what happens is that these functions, they blow up. So usually we see the system as being composed of some eigenvalues. This is a one way of seeing this, right? And this here has the time scales that we're talking about and the eigenfunctions. And these eigenfunctions blow up as we go to infinity. And the hyperboloidal comes as a parameterization that goes where we want, right? We go at black hole horizon, we go at Scri plus, and the conditions come that, well, these functions now become regular, finite, and because, well, we are precisely mapping where we want. So this is a background. I think perhaps everybody here is familiar with the motivation. But what comes in the field a lot of the times is when we have this feeling of, eigenvectors, a lot of intuition comes from quantum mechanics, for instance, or that we have a basis. Here it gets more complicated. To say that, well, is this a basis? Is it complete? All these questions are in the air. And for doing black hole spectroscopy, sometimes it's important to be able to project into the quasi-normal modes to see how a given function excites different modes. And people have been, over the past years, trying to come up with a way of finding some product, some bilinear relation, that if I join two QNMs, I get a delta function, essentially. So we can review this. There are here some of the main papers on the topic. And the main idea is, well, I want to construct a product between two functions. And essentially it's going to be integrating over the spatial direction. But the important thing is I have a notation that I'm combining the field itself with perhaps derivatives, time derivative, radial derivatives. I'm combining field and first derivatives and making a product with some coefficients along the way. with the function itself. But you might imagine that usually when we do this type of products, there is some sort of operation that enters in the second entry here. Just think about spherical harmonics. If I'm just multiplying two spherical harmonics to get the product, usually it's the spherical harmonics times the complex conjugate, right? There is an operation that enters into the product that many times is just complex conjugation. And here you're going to see that this is also a bit of the same structure. And well, what I want to tell is all this works usually as things goes. People first think in terms of the usual time coordinate. So these integrals are performed along a t constant. And we know, I just said, that if we consider Schwarzschild coordinates or Boyle-Lindquist, if we are in Kerr, these functions blow up, as I was saying. So we are going to be performing an integral over functions that are, infinities in this asymptotic region. And people find a way to get around and really evaluate those integrals. And what they do is that they deform the radial coordinate. They depart from the physical nature of this coordinate, which is a radial, right? They go into the complex plane. And by going the complex plane, they can find integration curves that makes the integral convergence and everything works nicely. And for me, this was always, come on, hyperboloidal has always been here because we are always pitching and selling this idea that, we solve all the blows up, we understand geometrically, we take them away, and then perhaps things get better, easier, and everything. So, and indeed, if we go into the hyperboloidal literature, there are works that were perhaps not writing things as a product. Well, apart from the most recent by José Luis and Hermie, and also a little bit, this was introduced by Edgar and then implemented by Hermie. They kind of think in this way, but previous works from me and Marcus, we were also in some way projecting functions into the QNMs. And in this context, we never needed to really regularize, because in this context, hyperboloidal, all these functions are finite, and all the manipulations that enters here were with finite functions. So not really needing to go into the complex plane. So the idea was, can we perhaps, if we think about these products, but thinking in terms of hyperboloidal, do we get things better? Do you understand? Can we get finite stuff? And we will see the answer towards the end. But to get there, let's see what is the symmetry that I was talking about. What we need to place in the. This is one strategy for this product, and within this strategy, I want to pay attention to what is this operation that enters to build up the product. So yeah, I think it's fair to say that we have seen this kind of relation, that every orthogonality relation, they kind of satisfy this property here, right? Because that's when we argue that if these two guys, they are different, then the product must be zero. We have the orthogonal part. But when they are the same, when the frequencies are the same, this is already the zero part. And and then usually the product is positive definite, so we can argue that the other part is not zero as well. So, and then this is how the orthogonality property comes into the game. Now, again, I'm going to insist in this particular strategy because there are people that think about this product in different ways. So, but this strategy uses conserved quantities to construct the product. And in our work, we kind of try to get the attention. People look, there are also fluxes when they talk about constant conserved currents in space-time. We have to be careful about boundary conditions and how things go. So we bring this attention. But okay, conserved quantities are entering the game. And this notion of conservation allows us to show that if I apply the derivative with the time, with the Killing vector over the product, Then I get a 0 because this is based on something that's conserved. And this 0 here on the right-hand side is kind of, it will play the role of the right-hand side here that we need eventually. So this is giving this part of the relation. Now one needs to try to get the left-hand side from a different way, from a different strategy. And the strategy is evaluating at a QNM. So this is valid, very generic. But at a QNM, we can try also to evaluate, and the QNM we know behaves like exponentially damped signals. So that's where we start to argue, like, okay, let's assume that the product is direct linear. We don't do anything. We just multiply this guy with that guy. We just multiply one by the other. Right? The product is the product of the functions as itself. Then what happens is that I'm going to get a sum of these frequencies. And if eventually I were to apply the time derivative here, this guy is going to be dropping. And that's the part where we compare, okay, right-hand side, we have the 0 coming in. This is the left-hand side. We compare both together, and we get that, well, this is not really the relation that we are looking for. So, I mean, going directly is not the goal, is not the game, is not how to go. If we were to try complex conjugation, as many other approaches does, for instance, for spherical harmonics, same thing here. So I say that the product involves the complex conjugation of the field here. Then, okay, I mean, I get a minus that's kind of flips the sign here, fair enough. But I also get the conjugation of the omega. And because omega is a complex quantity, it's not a real eigenvalue, then the product drops the conjugation. And again, if I compare both sides, it's not really what we need because this has nothing to do with QNMs at all. So again, complex conjugation is not the way to go. But what if we were able to just do a time reversal? What if I could just plug in this guy and change the sign of the t, right? So if we could do this, then I'm just changing the sign. I'm not getting complex conjugation. I apply the derivative. I get precisely what we need. And this is a kind of a green light for us to move forward. And this is a kind of a very back of the envelope argument for all these relations that enters the game. So yeah, I mean, what happens in this product is that we are given a solution to the wave equation. And then we act with some operation called this J here. That really, when I act there, it's going to be mapping the t to minus t. I'm going to be emphasizing on the t, but there is also the azimuthal part, phi to minus phi. So this product between two functions is the original function times the J operator acting on that. That is flipping the time sign. So this is the whole motivation to see like, okay, so now let's try to understand what this symmetry is so that we can manipulate them geometrically and move to hyperboloidal. So that's where we get in the second part of the talk to enter in this T-phi symmetry. And this is quite directly, right? If we just look at the Kerr spacetime, I have here the line element, the usual coordinates, and we want to get this T-phi transformation. It's just sending t to minus t, phi to minus phi, fair enough. I look at the pieces where this is going to affect. Quadratic doesn't change. Quadratic doesn't change. Quadratic, good. So yeah, this looks like a symmetry. Nice and easy, beautiful, fair enough. If I go to a scalar wave equation on Kerr, same business. If I go t to minus t, phi to minus phi, these terms here in red are all quadratic, we do get a symmetry. Nice. This is what's being called the T-phi symmetry. And I think for all of us here, the nice way to see those symmetries is if we go to the Penrose diagram, right? So I have selected here three surfaces within, so three T constant surfaces. One is the T0 as reference. One is the T with two horizons, 2 units. And the other one is -2, is the red one with the -2. And yeah, we have seen this in books and everywhere. So there is kind of a symmetry across the 0, the reference line here. One thing that I don't know. I mean, I've never seen much in books. I don't know how much people discuss this or how much this is spread, but it's also nice to see on the other side of the diagram, right? I mean, sometimes we forget that we can go to the other universe. In the other universe, there is this kind of a S shape here, right? I mean, the blue, that's the positive that goes up here, is going down there. And the red, which is the one going down here, it crosses and go up there. So there is also this kind of shape between the two of them. I think it's a nice feature to see and to keep in mind, especially because of what's coming in. And yeah, so the way I like to try to see the symmetries in general is I get confused sometimes when people write T2 minus T. I prefer to be very, very picky and really introduce like a right in terms of coordinate transformation. I really want to introduce something that I called here for today reversed Euler-Lindquist coordinates. I'm giving a prime for the whole thing. And this is just explicitly saying that T prime is the minus T. Because if I look at the diagram, and I look at a T prime constant, what we are getting again, the zero is the same, but the positive T prime is the blue, is the one that's coming down on this side, up on that one, and the negative T prime is the one that goes up here and down there. So if I look at them side by side, it makes sense, right? Because T equals 2 goes to a T prime minus 2 because it's just T2 minus T, and vice versa. And here the symmetry, again, it shows up very nicely, very beautiful. So to say, if I get somehow, I mean, there is some sort of symmetry across this part here, right? That up and down, I just flip them. But there is also the symmetry between the two universes, kind of. So an event here, through this symmetry, seems to be an event there. I've never really seen this interpretation. I don't know if people think in that way, if some people have this sort of intuition. But for me, it felt like, yeah, I mean, I mean, we are mapping this point into this point, perhaps. Is this a way of seeing? It could be. I don't know how useful, but yeah, sort of symmetry around here, around there, nice and beautiful, and that's why people call this a symmetry. But then I was asking myself, really? I mean, is this really a symmetry? This was still kind of there is, when you go to the hyperboloidal, how can we see the symmetry? Because if you go back to the wave equation, and now I'm going to simplify my life just to have less things on the screen. I'm going to go to Schwarzschild, okay? I mean, just take a rotation to 0. I'm also going to get the asymptotic behavior, just to get, the 1 over RDK, the harmonic decomposition, as we usually do, just to get a very nice and simple and easy equation for the eye, for visualizing this. And that's the point when someone very important comes into my mind, and this person says very sharp and very intelligent and very, smart and sentences. And this guy pops into my mind with some sentence that he said in Vienna. He said, well, so far we have an equation, but we don't have a problem at all. We don't have physics. This is just an equation, guys. I mean, where is the physics, right? Where is the boundary conditions? And because the physics enters when we put boundary conditions, when we close the system, when we make something that's well-defined. And the physical ones that we like to think is, well, the energy is propagating to the wave zone. The energy is propagating to the black hole is the one that we use and love. And usually we write them in this way, like as, well, the behavior goes as something. That's how you write. But we can also make things a bit more formal by taking the limit to infinity and expressing this in a differential form. And we can even use some vectors. I mean, if I have null vectors v and null vectors u, this gets a bit more geometrical form for placing these boundary conditions. And just recalling that whenever we are in this set of the equation, these boundary conditions, they enter as an external information that we have to provide apart from the equation, right? It's an external boundary condition that we have to impose. But when we impose these boundary conditions, we solve the system. Oh, there is a typo here, an ugly typo. Sorry. When we solve the system with these boundary conditions, when we solve this problem, because now we have a problem, we get a solution that I'm going to give a name. We get something that's the retarded field, right? That's what we are doing here. But of course, that we could also, I mean, this is the physics, but mathematically, we could just say, well, what if the energy was coming from the wave zone or from the white hole, right? If I have things coming from these infinities. I don't know if you noticed, but there was a plus here, a minus, now it's a plus. There was a flip in the signs here, and the V and U, they just changed roles here. So what we have now is I'm going to give a name for the solution. And again, sorry for the typo. We have here the advanced field. And that's where the question about, well, is that really a symmetry enters? Because when I do the transformation, T to phi, the equation is fine. The equation will have the symmetry. Fair enough. But the boundary conditions, right? If I'm thinking about the retarded field, this partial T here, when I apply to the whole problem, then by getting the transformation, I get a minus, an overall minus that is going to change this. So what this guy is saying is that, well, I started with the retarded, I get this transformation, and I get the advanced. So this J mapping, this J transform is really mapping different functional spaces, I guess. I don't know how to make fully formally mathematically, but it feels like, well, these functions, they are different, right? These functions, they are living different physics. And so is it really a symmetry or is it just an operation? And especially when you talk about the quasi-normal modes, right? So yeah, I mean, if I apply the J operation into the retarded field, what I get is advanced, and vice versa. And in particular, if we are focusing on the QNM problem, so if I start with a QNM that is describing the ringing down problem that we also use, in gravitational wave physics, this J symmetry is bringing us anti-QNMs, right? It's a kind of the one imposing the other boundary conditions. And I have just made up this word here. We are solving for the ring up problem, I mean, it's just because we are changing the boundary conditions with energy entering the system. So yeah, I mean, how to see this in the diagrams again? So I came to the question, is this really a symmetry? Because, yeah, let's go to the QNM problem, right? If I have, it's a bit slower on the screen. So if I have a QNM, that we decompose usually as the Fourier part and the radial. We solve this eigenvalue problem. We see that this functions here has the imaginary part negative that allows for the time decay. So it allows for this guy decaying as t goes to infinity, right? Because of this property, which is the same property that eventually leads the radial function to blow up at plus and minus infinities, geometrically again, because they accumulate in these 2 points. Now, the anti-QNM is very nicely described by the reversed Boyer-Lindquist, by the minus t property. Because if I make the Fourier transform with this reversed Boyer-Lindquist, I get exactly the same values for the QNMs. I get the exact same radial function. And I get the exact same behavior as t prime goes to infinity. The anti-QNM decays as t prime goes to infinity. And these functions, they blow up. So essentially, t is going up here in this part, and t goes, I mean, the coordinate goes, I mean, increases in this direction here. The t prime increases its values, the level sets in this way here, and increases in that way. So yeah, I mean, and the anti-QNM in terms of these coordinates is decaying as go to infinity. But if I were to get an anti-QNM expressed back in this time here, then there is a time change, the sign change here, which leads to the blow up as the ring up, as I was saying. I mean, it really leads to the blow up as because energy is coming in. So yeah, at some point I said, okay, I'm resisting to call this a symmetry. I'm going to go this an operation that's mapping these two different functions. After having this under control, that's when we said, okay, how then we try to get this from the hyperboloidal perspective, how this is going to enter. And of course, I don't know what's the most didactical way. I'm going to take the long road to get the final answer, but I hope you enjoy the journey to get the final answer through the longer road, which is, first I'm going just to define, just to give one possible definition for what I mean by future and past hyperboloidal. So the future hyperboloidal are the surfaces that geometrically imposes the retarded conditions on the regular solution. So if I'm solving the wave equation, regular solutions will be then satisfying the retarded conditions. Essentially, these conditions here, if I were to rewrite them in terms of a future hyperboloidal, they will be automatically satisfied. I'm not going to go to the details of the calculations, but we can really see that when we compactify the spacetime and we do the whole hyperboloidal conformal business, I can really evaluate this quantity here, and then I get a zero because everything behaves as they should. I don't have to impose this externally. Same thing for the past. These coordinates are going to impose the advanced condition on regular solutions. So it's the flip of the time here, or U with V, is going to be given by the past hyperboloidal. Again, intuitively, future is crossing black hole horizon and Scri plus. Intuitively, past hyperboloidal are crossing white hole horizon and Scri minus. So let's start trying to construct future and past hyperboloidal. And perhaps the first way that anyone with some experience in getting to the hyperboloidal world would say, yeah, I can just flip the sign of the height function that I'm choosing. So I have two choices here. So I have one that I'm calling tau plus and one time tau minus, and either or is going to be coming with different signs with respect to the height function. And here we need some care in, first of all, defining a little bit this notion of why I'm not going forward. Yeah, I have to define a bit of the notion of how to start with. And I say this because I think along the way, Anil and I had different sign definitions. And there are literature with different type definitions. So I'm going to follow something that I have always been used, meaning that in this notation, the T plus, the tau plus, is the one that I have always been using. So it's T, the T plus minus H, in such a way that T plus is always future. This is going to be the reference. The construction here plays the reference for one future hyperboloidal. And with that, I can sit down and calculate all the conditions. I can look at the surfaces. What happens is that the T minus is indeed a past hyperboloidal. So if I start here with a height function that gives me a future, if I flip this, if I change the sign of the height function here, I get a past hyperboloidal. However, and we can also map one into the other directly just by getting the notion of the height function. We have this 2 times the height function entering the game. And as I was saying, there is a however. If I look at the line element, and in our case, we go for the conformal world, or the conformal line element, what we see is that the sign in front of the dt d tau part also changes, right? So in this way, this transformation here is not really a symmetry of the line element. The metric is not invariant under the change of tau plus to tau minus. So this is clearly...
Just
yes?
one small... so when you say a future hyperboloidal time, that means it intersects Scri plus, and past hyperboloidal time means it intersects Scri minus. Is that it?
Precisely, yes.
Okay.
And on the other end, intersects the horizon, the black hole horizon, or the white hole horizon as well. Yeah, we are going to see this right now. So we are just going to see this right now.
Okay.
This is, I pick up a number, 2 length scales for the future hyperboloidal, and it's crossing the horizon, and it's crossing Scri plus as usual. When we do our business, we do our research, we do our work with that. When I construct with the same scheme, and I pick up the same number, the same kind of a level set for the time minus, as you said, I mean, Scri minus and white hole. But you see that in terms of cuts in the spacetime here, they are not really symmetric kind of between the original T0. So the symmetry here is not really appearing. This seems to be a bit later than that one, or in some sense. I mean, of course, this depends on how you compactify stuff, but the fact that they are different is another demonstration that even though tau minus is indeed a past hyperboloidal, it is not yet capturing this symmetry notion that the Boyer-Lindquist coordinate was giving us. And what I also found very interesting that I had never really tried to draw or anything is that if we go to the other side of the universe, in the same way that the Boyer-Lindquist kind of does, I was doing this structure here, that it changes when we move between the universes. The hyperboloidal on the right-hand side touches as we know, and the other side, it comes down here. And the same thing with the past. I mean, in this side, it has this H minus and Scri minus, and the other side, it comes here. So, okay, the message is we are constructing future and past, but we are not there yet getting the symmetry. So, a second possible operation, which I called time flip, and I think Marika is in the audience as well. She doesn't really like the time flip, I remember, but I'm going to get this. This is a time reversal as well. But here I want to insist with the flip because it's really just flipping the sign, It's just, picking up the checked coordinates just is the minus of the original one. And this has an interesting feature. For me, when I first saw, it was surprising, but quickly it was obvious that it's in this way, that this time flip, this time reversal in this way, preserves causality. In the sense that if I start with something that's a future hyperboloidal, and if I just flip the sign, if I just change the sign for a t checked to minus t, I'm also getting a future hyperboloidal. And if I have a t minus, which is originally a past, and I just change the sign, this is also a past hyperboloidal. When I saw this, is this correct? But it's quite easy to see that, well, this has to be, it's trivial because this time flip is with respect to a 0, right? So I have here, in gray, I have the tau 0. A positive tau is above the 0, a negative tau is below. So flipping the sign is just kind of switching these two here. So if I just flip the sign to the other coordinates, I'm just getting, the minus 2 becomes the 2, and the 2 becomes the minus 2. Or do I get this correct? I think there is a typo here again, right? Because this has to be, so if it's, or not, yeah, I think this is correct.
So
yeah, the one
Rodrigo,
above, yeah.
Do I understand correctly? Because basically with this flip, you're still sort of like staying within the same foliation. You're just changing the sign within the foliation, where in the other case, you'll be mapping between foliation, so to say.
Yes, yeah.
Okay.
I mean, it's perhaps within the same family of foliation, so to say, because it's if I start with a tau 2, the tau check 2, the positive tau check and the positive tau, they are different foliations, right? They are at different parts here, but they are within the same family. I mean, they are. And because the flip happens with respect to the 0, right? This is like it's happening just between the two guys here. Same thing with the past, right? If the flipping in the past also happens around some tau minus 0, then I just get the opposite of these two. But when you go to the conformal line element, this is where things starts to happen. So if I start with the future is my kind of standard definition, beginning with. If I'm just going to reverse the time in this way, if I'm just going to flip the time, I get from a plus here, I just changed it to a minus. Now, if I were with the past through this plus minus transformation, I had a minus here, and that was the break of symmetry between these two guys. And then if I flip the minus sign, I get a plus. So it sees that there is a symmetry, yes, between future and past, but in this direction, right? So I have to go from a future to a past with this plus minus business. But I also need the flipping sign to get into a line element that is symmetric everywhere. So the J symmetry here is acting in this way here. That's the action of the J symmetry, to keep a symmetry in some way, to be able to have a future and a past with a symmetric structure for the line element. So this is how I say that to construct, the time reversal. Now that I want to put a stronger emphasis in the reversal here, because this is the one that kind of gets the symmetry, that keeps the symmetry, which is, well, if I have some future hyperboloidal, and with that, it comes a notion, specifically when we have a background of associated height function. So I'm even saying the past foliation that leads to this reversal symmetry is the one that incorporates the 2H, but also flips the sign. So this is the transformation between the two. And this is where I said that I took the long road to get to this result, because if we know how to use our height functions that we've been using all the time, I could use the height function in the same way for the original Borel-Lindquist, as we always do. And I use also in the same way with the reversed Borel-Lindquist. So with the initial Borel-Lindquist, I get my future. With my reversed Borel-Lindquist, I get my past. And this is directly, because tau prime is minus t, this directly goes to that. So this would be a way shorter road. Get here, bam, this is direct. But I thought that the longer road kind of goes more into what intuitively I think many of us would start to be exploring in a very first approach. At least that's how I did. So yeah, when we have this mapping here, then the conformal line element, if I start with the future, I get the past symmetric, so to say. And if I look at the hyperboloidal, the foliations on the space diagram, if I pick up one particular number for the future, here I pick up the minus value just because it's a bit, longer. It's not so much here to the top. Then I start to see again this symmetry between all these worlds, and so the -2 in the future has the same shape just to the past. And
Can I
it also
ask something?
yeah.
If you just shifted the tau like previously without thinking about time symmetry and so on, you could probably do this as well. I would suspect that there is a constant shift of tau that you can pick for a given height function that makes this manifest in the conformal diagram. That the shapes are the same when you. Do you think that's true? I think that's true.
It could be, and it could be, but it could be that. So let's say that we have the as I call the original tau plus, and then let's say that I have the tau minus a tau minus star, right? I guess. So if this guy,
not just tau minus star, yeah, but I mean like the whole foliation. So the h, your capital H, the height function. The height function, whatever form it has,
kind of determines where tau equals 0 is. And that's true for tau plus and tau minus, right? And if you change the height function, that surface moves. Not just the whole of course the whole foliation also changes, but you can add any constant number to the height function that will switch them both, and that will change their location in the Penrose diagram. And then you can adjust the two by just changing the height function, actually, by a constant term. I'm not talking about just shifting the tau minus. I'm essentially talking about shifting both.
But a constant term in the height function is the same. I can think of shifting the orange of the tau as well, right? Yeah, the orange of the tau somehow as well.
Yeah, but then you're shifting both of them.
Yeah. So what I suspect is, in the end of the day, whatever you are doing, so is you are going to either be shifting for the plus and adding. If you have something, then you are going to your tau star is going to be minus 2 times the tau that we are, so that the plus goes to a minus. And I'm assuming that I always have the same height function in both cases, so to say. This is the starting game as well, right? So I don't know, because also with a constant, if I go back, no, I want to go back. If I go back, how do I go back here now? Why am I not going back? Okay, I'm going back here. There is the question of how the line element is going to change. I mean, if we are just
Well, but the thing is, if it's just shifting by a constant, I mean, what enters the line element is always the boost, so that constant just disappears.
Yeah, the constant disappears for sure. I mean, but if I'm just adding a constant to the somewhere here, then I'm not going to be changing the nature of the. Yeah, I mean, I don't know if this is going to be doing the whole. Because you say you would be needing, if I go back to the other plot, this plot here where they are different, right?
Yes,
the ones that
that's
they are
what
different.
I mean. So if you go back to
So
yeah,
this one where they are different,
exactly.
yeah. So you say
I think there is a constant shift in which those two, the blue and the red, will look the same.
Yeah. So but I think that I agree that I could place a shift here, right, to bring this guy and be symmetric to that one. I think this constant, and again, let me call whatever constant. This constant is going to be minus 4 RH or something to make this a plus or minus, to make them to cause the time, because this is a 2, somewhere there is the 0. I just have to swap across the 0 to reach there. This constant might be dependent on, it's not really a constant, it might be a function of tau hat, right, or tau minus, because it might depend on which level set we are picking. It's not going to be the same for all of them.
But if you apply a shift to both of them, eventually they will slide, and then the red will look like the blue, and the blue will look like the red, and at some point they will meet.
I think in the end of the day, if we do this systematically, I'm quite sure that you will end up with a generic transformation that is that in this constant, I think it will be eventually absorbed in a way that you end up with that thing. I mean, with this property here, it's going to be showing up somehow with this manipulation.
Yeah, I think it's equivalent. That's what I mean.
Yeah.
Okay, thank you.
So yeah, and so when we have this kind of structure, the regular representation here, the one that we always use for the retarded field, for the QNMs, we go into the hyperboloidal coordinates, and then we get our decay in time with a regular function. If I get an advanced field, or the anti-QNM, with the past, again, this is going to be regular, because sigma check 0, for instance, for me is scry minus, 1 is white hole. And so these are all regular representation of these quantities within their kind of best adapted coordinates, let's say this way. But if I want to represent the advanced solution in terms of the future hyperboloidal, then the transformation that enters is going to be flipping the time, making this guy rings up with time. And it also brings a divergency into the radial piece, because it's like trying to resolve with a coordinate that's best to describe I'm tired. It's trying to describe something at the horizon, at the black hole horizon, a feature that is being that's coming from the white hole. So, and this is doing the business there, which means that now, I don't have it here, but if we are doing the product between two functions in this business that I was talking, and we are at a hyperboloidal, at a tau hyperboloidal, and this is the product of the advanced field in the tau times the retarded field in the tau. It means that, well, we managed to resolve the blow up of this guy that people previously were having, that we resolve as we always do, but we shift the blow up to here. So we don't fully remove these blowing ups in the product, because this time reversal is an essential feature of this particular strategy. So we still rely on this quantity, and we have to resort to some tricks. I mean, we had to. So yeah, with that, I think I am done. Yeah, that the idea was to introduce this time reversal within hyperboloidal by bringing future and past foliations. My motivation was to construct this bi-orthogonality project in the work with Marika and Laura and Cristiana. As I just said, I mean, now from this perspective, the product with this strategy is always pairing a QNM with an anti-QNM. So hyperboloidal, good for here, not so good there, still blowing up, and yeah, therefore, does not fully remove these blow-up factors. And with that, I finished, well, with 10 minutes maybe. Thank you so much.